Hello, everyone. Thank you for attending my virtual talk on the sensitivity of Antarctic sea level records to late Holocene glacial fluctuations. I wish we could be meeting in Tasmania, but that's not what life brings us today. Before I get started, I'd like to acknowledge my co-authors, Julie, Cameron, Brittany, Jeannie, Chris, and Lauren. So, I'm speaking to the choir here, but as many of you know, the Antarctic Peninsula is one of the most rapidly warming places on the planet. As a result, we're seeing retreat of tidewater glaciers, the collapse of ice shelves, including the Larsen B in 2002, which we'll mention a little bit later, changes in ocean currents, wind patterns, and even biological activity. Now, in order to place these current changes into context, it's important to look to see how the ice sheet has changed in the past. So how do we go about doing that? Well, the first thing is we need to reconstruct the ice sheets through time. Now, one of the most direct ways of doing that is to map the extent of the ice sheet through time, looking at things such as moraines and trim lines. Now, many of these are offshore, some of them are on land. Now, when mapping these, this gives us the geographic extent of the ice sheets, but not necessarily their thickness. So one way at getting at the thickness of the past ice sheets is to look at records of relative sea level change and use those to constrain or calibrate glacial isostatic adjustment, or GIA models. GIA models are basically numerical predictions of the deformation of the Earth, both the solid Earth deformation, as well as changes in the sea surface height due to changes in the gravitational field of the Earth due to the growth and decay of these ice sheets. These GIA models are important not only for reconstructing past ice sheets, but also for predicting future spatial variability in sea level rise, as well as correcting satellite-based estimates of the mass balance of ice sheets, and particularly those that rely on gravity measurements. Now, one thing, we'll see that most current GIA models are relatively simplistic in their assumptions about not only the growth and decay of the ice sheet, where they basically assume a continual decrease in the size of the ice sheet through the Holocene, but also the response of relative sea levels to that. So here's one such model, a great model by Pippa Whitehouse in 2012, that shows largely shows a decrease in the rate of RSL fall through time. Now, what we're going to do is basically see how accurate that is of a monotonous exponential decrease in the rate of RSL fall through time. Now, the reason I'm sort of bringing this up is that as there's this growing body of evidence that Holocene climate has fluctuated through the Holocene. And as a response to those changes, those Holocene climate changes, the ice sheet, locally, what has been left of it, has actually advanced and retreated during the Holocene. And evidence for that comes in moraines such as this, the Shetland 1 moraine on Livingston Island. And so the question I want to address is, did these oscillations, these climatic changes in the late Holocene, influence the RSL record of the Antarctic Peninsula, such that maybe those GIA models showing a decrease in the rate of RSL fall through time maybe aren't that accurate? Well, the short answer is yes. I'm going to try to show you evidence for periods of increased RSL fall and possible transgressions during the Holocene. Now, one thing in a couple places, particularly when I compare our RSL records to GPS uplift records, we need to understand that there's a slight difference between uplift and RSL fall. RSL fall is not only uplift of the land, but also changes in the elevation of the sea surface height. Now, to go back and forth between RSL records and uplift records, I basically have corrected for sea surface height changes. And I do that using a GIA model. Now, that might seem circular, but one thing I want to point out is that the sea surface height changes are minor. They're a few tens of centimeters compared to the meters of uplift over these time frames that we are experiencing. So how do we reconstruct RSL across the Antarctic Peninsula? One method has been isolation basins. The other method, and the one that I'm going to focus on in this talk, is using raised beaches. Basically, as the land came up, we had left with these old beach ridges up the sides of the hills. If we measure the elevation of the modern beach ridge with respect to modern sea levels, we can subtract that from these old beach ridges to get the elevation of sea level at the time that the beach ridge is formed. Now we also need the age, and we get the age from either radiocarbon dating of bones, shells, and seaweed, or optically stimulated luminescence or OSL dating of the cobbles and sands within these beach ridges. So I'm going to show you two examples where we think that the rate of RSL fall increased during the Holocene, and then two examples where we think we saw a minor transgression within the overall fall. Now the two sites that I'm going to show increases in the rate of RSL fall are Joinville Island and Torgersen Island. Now the first one, Torgersen Island, is important because we have a nearby GPS record since 1998 that allows us to sort of compare uplift rates in ongoing to sort of longer term Holocene RSL changes and hence uplift rates. Now what's interesting is the GPS station at Palmer Station showed a rapid increase in the rate of uplift following the collapse of the Larsen B ice shelf. This was likely due to the buttressing effect that that ice shelf had on the glaciers that then accelerated after its collapse. And as it accelerated, we lost mass and the land came up. So on Torgersen Island, not less than a kilometer away from the GPS base station, we see two raised beaches, one at 7.2 meters and the other one at 5 meters. We dated these and get ages of about 800 and about 1500 when waiting for the error when averaging these two ages. And using the modern beach ridge, its elevation and zero, we can come up with uplift rates averaged over a couple hundred years. And what we can see, this is time in years before present. This is uplift rate in millimeters per year. Again, the RSL record has been corrected for sea surface height changes to come up with this. And what we see is an increase in the uplift rate at about 780 years. So this is the 7 meter beach to the 5 meter beach, the 5 meter beach to the modern beach. And that the rates throughout the Holocene averaged are on par with the uplift rates experienced after the breakup of the Larsen B, and an order of magnitude higher than the uplift rates recorded in GPS prior to the breakup of the Larsen B. Now, this isn't the only site that shows increases in the rate of RSL fall or increases in the rate of uplift within the Antarctic Peninsula. Our second site here is in Joinville Island in the eastern Antarctic Peninsula, where we have 18 very well-developed, or 31 well-developed beach ridges. The lower 31, or lower 18, excuse me, fortuitously contain mats of seaweed interbedded with the beach deposits. What's nice about that, we can radiocarbon date them. And fortuitously, this never happens, all the raised beach radiocarbon ages are in stratigraphic order. Here we can see this is the 18 meter beach down to the modern beach. This is relative sea level above present day after correcting for the modern beach elevation. And what we can see are these topographic breaks in the beach ridges that correspond to rapid increases in RSL fall or uplift. One of them occurs within the last 500 years, so similar to the time frame seen at Torgersen Island. Another one about 1500 years ago, and then a potentially older one at 2200 years. So we see these increases in the rate of RSL fall, not only at Torgersen Island, but also within Joinville Island. Well, what about the other one? Examples of local transgressions or periods of RSL rise during the overall fall in relative sea level experience through the Holocene. Now, these are harder to preserve because generally during transgression, we get erosion of the beach rather than deposition. Furthermore, continued RSL fall later is going to bury any sort of beaches formed during this time period. So we actually turn to ground penetrating radar to see underneath the beach ridges to see what we can see. So again, we're going to go to Joinville Island on the eastern Antarctic Peninsula and then Livingston Island on the South Shetland Islands. So here is that Joinville Island data set. These are those beach ridges with those topographic breaks that represent the acceleration in the rate of RSL fall. And what we can see is what we typically see during a prograding beach deposit, which is generally what we see during RSL fall, which is seaward dipping reflections. However, within the last 400 years, we actually see a change in the GPR character, where we get an erosional surface unlapped by landward instead of seaward dipping beach ridges. In addition, as we can see through most of this time period, we get a beach ridge formed about every 100 to 150 years. But we're missing 400 years of beach ridge development here between about 700 and 200 years ago. Now, this isn't the only place that we see buried evidence of erosion within beach ridges. Here within the south beaches of Livingston Island, we generally see an overall progradation or seaward dipping reflections, but it's interrupted by a couple prominent beach ridges that show landward dipping reflections overlying a erosional scarp. Now, this erosional scarp is at the base of our GPR data, but fortunately, these same beach ridges have streams cutting through them, and we're able to see sort of the subsurface data. And here we can see the bedrock with what appears to be an erosional scarp, maybe even a paleo sea cliff that then has been buried by ongoing beach progradation. This is oceanward and this is landward. So what's causing these erosional surfaces or the development of these scarps? Well, what we think is happening is this is the result of minor transgressions. In that during the overall RSL fall, we get this sort of offlapping succession of beach ridges that form. But then when sea level starts to rise again, we erode back through those earlier deposited beach ridges, hence the hiatus in beach ridge formation. Then when the transgression is over and RSL continues to fall, we then get renewed progradation and burial of that scarp. What could be driving these transgressions and then the later accelerations in RSL fall? Well, we think it is controlled by this glacial advances and retreats. When the ice advances, we depress the crust, which causes a local RSL rise. When it then retreats again, we get an accelerated RSL fall. The most recent set of that transgression and an accelerated fall occurs at about the time of the Northern Hemisphere Little Ice Age, which we do find some evidence throughout the Antarctic Peninsula for such an advance and retreat. Now, this kind of follows from an earlier study we did in 2002 that suggests if such fluctuations are occurring, it would require a relatively weak Earth rheology, which is not what most current GIA models use for the Antarctic Peninsula, but one that is required to fit the known glacial retreat, or excuse me, acceleration in retreat of the glacier following the breakup of the Larsen B. So in summary, multiple sites across the Antarctic Peninsula are showing advances and retreats, are showing accelerations in the rate of RSL fall, as well as periods of RSL rise, the most recent occurring around the time of the Little Ice Age. That would require weaker Earth rheology than most traditional GIA models, which means maybe we should reevaluate what some of those GIA models are telling us about, for instance, the extent of the ice during the last glacial maximum. So in summary, I'd like to thank many people, the NSF's Office of Polar Programs for funding. Many people helped getting us into the field, as well as while we were in the field. John Southern helped with the radiocarbon dating, and I'd like to acknowledge Eric, Pippa, and Grace for discussions related to GIA. Thank you for your attention, and have a great day.